Welcome back to our YouTube channel. Today we are met by this question which wants us to evaluate the integral from 0 to 1 of sine ln x over ln x dx. Now this is a very cool integral because it uses both U-substitution and the Feynman technique of integration to solve. And I solved this integral pretty recently and I thought it was cool, so I wanted to share it with you guys. So let's get right into it. First things first, let's do the U-substitution and let's do it in our corner here. So let's let u equal negative ln x. Now the reason we equate u to negative ln x instead of ln x is because later on we're going to take the limit as a variable approaches infinity, and we want an exponential function to become the denominator and drag down the entire function to 0. So if that doesn't make sense, later on you're going to find out why we used negative ln x instead of ln x. Anyway, this implies that x is equal to e multiplied by negative u, which implies that dx is equal to negative e multiplied by negative u du. Now, let's see how our bounds change. So when x equals 0, u will equal infinity. Now, the reason for this is because if we plot the graph for ln x, we're going to get this. There is no negative side because you can't put a negative number inside the ln function, so we can only approach 0 from the positive side, and as we approach 0 we approach negative infinity, so we can say 0 is equal to negative infinity. But since we let u equal negative ln x, it's actually going to be infinity, because negative multiplied by negative infinity is infinity. And if we take x as 1, so we can find our other end of the bound, we're going to get 0. So these are our new bounds. Let me just erase this little graph here, and let's rewrite our integral now. So here we have the integral from infinity to 0 of sine negative u all over negative u multiplied by negative e to the power of negative u du. So let me just erase the working out here because we don't need it anymore. So this is our new integral. So how about we simplify this? So notice that inside the sine function we have negative u. And since negative u is in a sinusoidal function, we can actually remove this negative and put it outside the function because of how it's symmetrical. And this negative will just cancel out. So we're going to have sine u over u multiplied by negative e to the power of negative u du. Now, another thing we can do is actually take this negative outside because it's just a constant. And remember, the negative of this function, we can just remove this negative by flipping our bounds. So after we do all this, we have the integral from 0 to infinity of sine u over u multiplied by e to the power of negative u du. Now, here is where we implement the Feynman technique of integration. So let's create a function and call it I. And let's add a parameter called t. So I of t is equal to the integral from 0 to infinity of sine u over u multiplied by e to the power of negative u t du. So notice we put our parameter in the exponential position of e. Now notice if we take t as 1, we are going to get the same as our integral here. So we can say that this is equal to I of 1. And remember, this is equal to this just in terms of u, which means this is also equal to I of 1. Okay? Now, we want to find the differential of this function here. So let me write it down here. I dash of t is equal to, now if you watched my previous video on the Feynman technique of integration, you know that we can use the Leibniz integral rule to differentiate this integral here. So we're going to have the integral from 0 to infinity of, now let's evaluate what happens here. If we take the partial differential with respect to t, we treat this as a constant and we treat this negative u as a constant. Meaning when we differentiate, we're just going to get the negative u term multiplied by everything here. And that u part of the negative u is going to cancel this u, and the negative we can actually take out. So here we're going to have the negative integral from 0 to infinity of sine u multiplied by e to the power of negative ut du. Now, we can actually evaluate this integral using integration by parts via the tabular method. Let's divide our board here. So, this is equal to, let me put square brackets here. It is equal to e to the power of negative ut multiplied by cosine u plus sine u multiplied by t, I forgot the t here, all over t squared plus 1, let me close this bracket and close the squared bracket, from 0 to infinity. So, let's take the limit as u approaches infinity. Remember, we said that we wanted an exponential function to become the denominator and drag everything to 0. So that's what's going to happen here. This, because it's the power of negative something, it's going to go down into the denominator. And since it's the power of infinity, it's going to go so high that the entire function becomes 0 because the denominator is so high. So we're going to have this is equal to 0 minus. Now, what if we take u as 0? If we take u of 0, we're going to get 1 over t squared plus 1. So, I dash of t is equal to negative 1 over t squared plus 1. Remember, I of, this means that, okay, so now we have I dash of t, and this is equal to this. But we want I of t, not I of dash of t. So we're going to have to integrate this. And since the negative is just a constant, we just took it out. So when we integrate this, let me just remove the 0 and the equal. We're going to get, well, wait. We're going to get negative arctan of t plus c. This is, by the way, integrated in terms of dt, obviously. So we're going to get this. Now this is I of t, not I dash of t. So let me put that here. I of t is equal to this, which is also equal to this. But we need to find what our constant here is. Now remember, I of t also equated to this. So, what if we equate them both together and take t as it approaches infinity, so this drags down to 0, and see what this will equal? Well, believe it or not, if we equate both of them together and let t approach infinity, we're going to get that our c is equal to pi over 2. Now, we're really close to the answer. Remember that our integral and our main question is equivalent to I of 1. And this is I of t. So what if we take I of 1? So what if we plug in t as 1? We're going to get negative arctan 1 plus pi over 2. Let me just put pi over 2 here so nobody gets confused. Pi over 2. And if we take t as 1, this is all going to equal pi over 4. And that's our solution to this question. Very cool, no? Thank you for watching the video. I hope you learned something new. Bye-bye.